But yes, last week we talked about this formula in particular and how to set up a confidence interval proportions. So this week we're going to be talking about means. And just to remind us so that we can all remember where it is in your lab manual, there's a section called Technology Overview. On this particular version, you'll see it's on page 93. It can vary by a page or two there. But around page 93, you'll have all the new formulas and how to use them in very technical terms on that page. And so today I'm going to show you and explain to you this bit of nonsense and how to use it and set it up and that kind of stuff. And so I'm going to jump into the spreadsheet now, where I just took a screen capture of those particular parts so we can focus in and remind us that we're talking about means. And so we will need to remember in some cases the old formulas that were associated with means, namely average and standard deviation. So one thing to remember from last week is error here, that we often just call error, is known as the margin of error. And the margin of error is defined as a critical value, so I'm going to call it crit for short, times standard error. And so we should all recognize this part here on the right. That was from unit 2, right? That is the formula for standard error. Therefore, in this context, this T alpha over 2 is our critical value. Now, one nice observation to notice is whenever we do an alpha over 2, let me jump back to that document real quick. These alpha over 2s are always indications that we're talking about critical values. And so we can always identify whether it's a z-score or this thing that you're going to learn about soon called a t-score. And so both of these things, because you have the alpha over 2, we're talking about them as critical values. And so they're very important in terms of confidence intervals. But there's actually some cases that we'll do not for confidence intervals, but with hypothesis testing, where we don't do this alpha over 2 aspect, and it's just an alpha there. That's neither here nor there. You'll learn about that when you get to hypothesis testing. But just know that this is one big clue that these things that we're talking about are known as the critical values. And so margin of error will always be defined as a critical value times standard error. And just notice that it depends if we're talking about means or proportions on what these things are. For proportions, our critical value was a z-score, and our standard error was the square root of pq over n. That was, we're talking about proportions. When we're talking about our averages, critical value is done by what we call a t-score, and you times it by our s over root n. But in each case, it's always some kind of critical score by something we define as standard error. And so just knowing which one you're dealing with will help you with what kind of situation you're dealing with. And so today we're going to be focusing solely on this portion. I say solely, I actually snuck in a proportion question on there so we can learn how to kind of differentiate the two. But in general, our bigger emphasis will definitely be on the margin of error for means. And so notice T alpha over 2 is defined right here. We're going to use this first formula because, of course, we learned last week that this C here is referencing the confidence level. And since you're doing a confidence interval, it makes sense to utilize the formula that has confidence built into it. And so we're just going to use this really rather straightforward formula, and I'll demonstrate that in a little bit. And then we already know how to do the right calculation, the standard error calculation. That's just our standard deviation, which if we need it, there's a formula down here, divided by the square root of the sample size. And we know by CLT, we can do this in any case that we have a normally distributed or large enough sample, we can utilize this kind of standard error, right? Because when CLT applies. Okay, enough of me blabbing on. Let's actually get into setting up our calculator so we can then learn when we can and can't use it and how to best use it in different situations. So like last week, we learned that these yellow boxes, those are our inputs, and the white boxes, those would be our formulas. And so we'll see to do the confidence interval for means, we need 4 inputs in order to do them. Unlike last week when we did proportions, we only needed 3 inputs. And we'll see all that in action, of course. So the first calculation that we'll need to set up is our standard error calculation. But of course, we learned that back in test 2. That is nothing more than our standard deviation value divided by the square root of how big the sample is, the sample size. And then we need our t-score, which is our critical value. It's just we're talking about the t-distribution, and you'll learn how the t-distribution looks and works and all that in class. I'm just showing you how to set up the calculation. And so again, the t-score is just this formula right here, the t dot inverse 2t and all that stuff. And so let's do it. Equals t dot inverse dot 2t. And I know, I forgot. Let's make my font larger. So just in case you didn't see it, it was b2 divided by the square root of b3. But now, t dot inverse dot 2t, 1 minus the confidence, which is the square above. And then degrees of freedom, you'll learn more about what it means in the class. But degrees of freedom is just defined as your sample size, take away 1. For this class, it will always be take away 1. In some cases, it's not always take away 1, but for this class, that's just how we define degrees of freedom. So that will give you your t critical value. And we know margin of error is always defined as your critical value times standard error. So those two calculations we just did. And then remember what a confidence interval is. It's some center minus our error calculation. That's our lower level. And then some center plus our error calculation. And by error, I mean margin of error. And so in this case, our point estimate or center is the mean. So we have the mean minus the error, and we have the mean plus the error. So this is your lower level. This is your upper level. There we go. And so if we want to get our values, then we're going to say our center, which is our mean, given the very top, minus our error that we just calculated. And then we'll have our mean plus our error that we just calculated. And let's just throw in some random numbers to make sure everything is set up properly. Let's say we have a mean of 12, deviation of 1.2. How about a sample size of 40? And I want to be 95% confident. And we can see things start populating through. And so it seems that numbers are making sense. Obviously, we won't really know, but your numbers should match my numbers at least until we get practicing some questions and obviously getting error messages or whatnot. But this is the general idea of what we're looking for. And so notice as you fill in the yellow boxes, it automatically calculates your standard error, automatically finds your critical value, your margin of error, and then it does the easy calculation of your lower level and your upper level. So remember the whole point of this kind of calculator, though. The point of this calculator is to determine the error, determine the margin of error. So if they give you the margin of error, you don't need this calculator. That's the whole big idea. So some questions, they're going to just give you the error, and you're going to try to plug things in here and it won't work because you're not really giving all these 4 bits of yellow box informations. You don't have all the 4 boxes of information. You're just given the margin of error. So you have to know when you have the margin of error, just run through and do the calculation yourself because they already did and kind of did the hard work for you. Check the chat real fast, make sure I'm not missing anybody. Hello to those who just showed up, or maybe been here for a minute, hear me babbling on. But anyways, we now have a calculator set up, and we learned last week we can copy and paste this calculator into the questions itself in order to answer the questions, and all of our formulas will stay intact. So let's actually look at our first question and see if we need it or not, and decide. And of course, if you're reading backwards, like I always encourage you, if you start at the bottom, you'd see they're already telling you the margin of error. That means we do not need the calculator. The calculator's whole purpose is to calculate the margin of error, but they already did the work for you. That means we just take our center, our average, and we subtract the error and add the error. And so in the margin of error form, that's one of the 3 ways we can represent it, right? The margin of error format. We would say it's 4626 plus or minus 590. And that's one way of representing a confidence interval. It's not the most common way for this class. For this class, we tend to prefer interval notation. Most of your homework's going to want it that way, but they can switch it up if they want to. But to get the lower bound and upper bound, that just means you have to carry out the subtraction and carry out the addition. We're going to do two different problems. So what we're going to do is 4626 minus 590. And then we'll go back and do it again and do 4626 plus 590. And so writing an interval notation is simply as 4036, comma 5216. It's quite literally just adding and subtracting the margin of error. That's the whole point of a confidence interval. Find your error and then add and subtract from the center. Kind of like what we do with the usual range. So now we want to talk about the boundary format, the inequality notation. You just start with a smaller number. And we say it's less than our middle, which in this case is an average value, which is less than 5216. And so these three formats are the three different ways you can represent a confidence interval. We can either do it in the margin of error format, we can do it by our interval notation, or by the inequality notation. They're all legitimate and they all actually mean the same thing. So what exactly are these saying? It means with some level of confidence, we know the actual average bill for the population is between these two numbers. We have no idea where it is. It could be as low as $4,036.01 and as high as $5,215.99. All I know is between those two values. So I can confidently say it's higher than $4,000 and under something like $5,300. So I can confidently say that, but I don't actually know what the actual number is for the overall population. It's just between those two numbers. But I made a very narrow bracket. And just to remind us, when we say confident or confidence, we're not actually talking about the probability of getting the population correct. We're talking about the process. And so if you're like 95% confident, you're 95% sure that the process we used, this method of calculating margin of error, using these yellow boxes to find the margin of error, that process works 95% of the time. There are other methods that are completely different that calculate a confidence interval in a different way. We are talking about this particular method and how well this method works. And so by saying the confidence level, you're just saying whether or not the method is a good method or not. Okay, let's pick apart what we do know. We see a lot of key things. I see a survey of 40 PC owners. So that's referring to, of course, our sample size. That's nice. And then we see this phrasing of between two measurements. And then, of course, we have our confidence level. And they want to know the point estimate, our center. Well, if we're between two measurements, that should be a big red flag that we're saying that the value we want is between these two measurements. And so we're essentially talking about this being our confidence interval. So for a confidence interval, it will always be our sample center. I know I didn't say sample before, but when I said center before, I meant sample center minus your error, and your sample center plus your error, which means that you're starting off with your sampled center in the middle, and we subtract an error and we add an error, which just means that if you want this point estimate, if you want that center, you just need to find out what's in the middle of your two endpoints. AKA, we just need to find the mean or the median of those two numbers. It doesn't matter which one we use because when you only have two numbers, the mean and median will always be the same thing. And so if you want, you can simply say the average of 3.4 and 4.0 like this. Of course, I have the other option. If I want to, I can say the median of 3.4 and 4.0. Or if I want to be old school, I can bust out the old arithmetic method of adding the two numbers up and then dividing by 2. They all mean the same thing. So pick the method that makes the most sense for you and run with it. But essentially the center, the point estimate, the average in this case, is 3.7. Now notice I'm going to say X bar, and I'm not actually going to say mu. Why is that? Well, we don't know the population. This is an estimate of where the population is. It's anywhere between these numbers. The only thing that we know is in the center of an interval is the sampled center. So we know that 3.7 was a sample from these 40 people, but we don't actually know where the population resides. Because what you do is you find the sampled measurement and you minus an error and add an error. Now it's not asking me, but what if it wanted to know what the margin of error is? Well, if 3.7 is the center, how far do I go to get to 4.0? How much would I need to add to it? Well, when in doubt, we can simply subtract the two measurements, the center and the upper extreme. We could say 4.0 minus 3.7. And we get 0.3, and that should make sense because 37 plus 3 is 40, and 37 minus 3 is 34 if you ignore the decimal, essentially. And so you can find your margin of error as well when you know one of the facts. All right. A question now, finally, where they don't give us the margin of error and we actually get to use our calculator. Reading bottom to top, you'll see from this last sentence right away, you're constructing an interval with a 95% confidence level, and you want it for the means. So we're going to go back to our calculator, grab our information by just highlighting, and copy, and jump into the problem to paste it somewhere that we like. How about right here? Doesn't actually matter where you paste it. And let's maybe bring our stuff back by deleting a couple columns until our data comes back. There we go. And yeah, I copied the data for you because obviously this is a picture and we can't select numbers from picture. So might notice a couple problems though. In this case, when you read the question, nowhere in the question is it literally telling you the mean. So we need to derive that. Likewise, there's nowhere in here telling us the standard deviation. So we need to derive that. That's where the formulas you learned way back on test 1 come into play. So they're going to expect us to know to go to equals average and then highlight our data. You could, if this was clickable, we'd highlight the values in here. Otherwise, if all your data is in a beautiful column like this, you know, you can just click the column letter at the very top and it will highlight all the numbers for you. But there's the average of the data set. In this case, we are talking about a sample, and for confidence intervals, we're always talking about a sample. Why is that? Well, if we're talking about a population, then we can tell you what the center is. It's just the average of the values. There's no mystery. It's the center, it's the center, it's the value that you get from the population. But in this case, we always have a sample involved because we don't know what the center is. There is a mystery, and so we need to find standard deviation. You know, always be .s. Because we're talking about a sample. I know in unit 1 we had .s and .p, but it's always going to be .s for test 3. That's the good news, one less thing to worry about. So standdev.s, click in my column, hit enter, there we go. Now in this case, we actually know the sample size. It's told us right here, but sometimes it won't tell you, and it can be a pain to go through and count all the numbers, especially if there's a lot of numbers. So just one little fact that's nice to know is if you want to quickly figure out how many numbers there are, it's as easy as going equals and the word count. That will tell Excel to count how many numbers there are. And so you click on the R in this case, because all my data is in R, close my parentheses, hit enter, and it counts it for me. Now, obviously, if it tells it to you, you don't need that formula, but it's a nice fact when you have like a long list of numbers and you don't know how many there are. And the cool thing about this is it only counts numbers. And so if I add words down here, like happy, it still says 20, right? But if I add an extra number, it now says 21. So it only counts numbers. That's the good news. So if it has a column title, like, you know, measurements or whatever, it won't count that. Okay. So now we have the standard error calculation already automatically done. And so we just need our confidence level. And of course, that's given to us, 95%. And we know if they don't tell us, we assume 95% as a default. But there we go. All of our calculations are now done, so we are ready to write our confidence interval. The minimum value is 149.03, and the maximum value is 193.47. And these are considered exclusive, so any value between these numbers is accepted. So in this case, if I wanted to interpret it, I would say I am 95% confident the true population mean number of pages is somewhere between 149.03 and 193.47. And it's okay that they're decimals because we're talking about a population mean, and means, of course, are continuous. They can have decimals. And so I'm saying if you went to find all the books in the universe of books and found the mean number of pages, that mean is somewhere between these two values. No idea where it is. It could be way down near 149, or it can be way up there near 193. I just know it's more than 149 and it's less than 193 with 95% confidence, which of course means 5% of the time this method won't work. Okay. So we start at A. I hope you're starting at the question. You'll immediately know what to do. We're going to find a confidence interval for the mean. So we're going to go grab our calculator, copy. I'm going to erase that little dot because it keeps copying that dot too. And now I'll come back and paste it somewhere. How about I paste it over here to the right this time? Whoops, a little too far to the right. Right there. Okay. And I'll paste it on level with my question. Great. And once again, we're not given in the problem the mean or deviation, so we need to calculate it. But that's easy enough. That's equals average. Click on the column or highlight your data, however you like to do it, and get your average. Standard deviation, that's the standdev.s. Parentheses, click the column, get your data, boom. We're told right here what the sample size is, but again, if you didn't know it and it wasn't obvious, just say equals count and get how many data points you have. Either way. It's also a good way to check your work because if you're actually manually writing these numbers in because they give you a picture to work with, you can check and make sure that you actually have 71 data points to match what they're saying and how many data points you have as well. And so our confidence level that's given to us is 99%. 99%. And there we go. We are 99% confident that the average household has a level of between 2.79, how about I just round it to 2 decimals, and 11.79 become 80, right? If I round to 2 decimals. And again, we don't have to do that in our heads. We highlight, we can just tell Excel to do that rounding for us. I just went to 2 decimals though. There we go. And so based on this information, we're finding the confidence interval for mean lead content in the population of residents in Flint, Michigan. So it was a big controversy back in the late 90s, early 2000s that people in Flint, Michigan were drinking poisonous water. And so they wanted to know what was the average household's level of toxicity, how much lead was in their water. And so we're 99% sure that it's anywhere between 2.7 and 11.8, the average value. So now we're going to use this interval for something. And it says that the CDC says anything greater than 15 is essentially toxic. And so based on our information, is it likely that the mean lead content of our households is greater than 15? Well, we don't know what the mean is, but we're 99% confident in our method that it's somewhere between 2.7 and 11.8. So would something like 15 make sense? Is 15 between these numbers? Is it really possible? Based on our findings, we're going to say no. It is not likely. It is not likely. I cannot spell. It is not likely. Let me just write it again. There we go. It's a little better. Still trashy, but better. It is not likely to be over 15, right? Exceeds means over. So it's not likely to be over 15. Just clean that up a little bit, make me feel a little less insecure about my writing. There we go. Yeah, so all we're saying though is that's not likely to be over 15. Now, do we know what it is? No, it could be down as low as 2-ish, or it could be as high as almost 12. So it appears to be possible that it's dangerously close, but it does not appear to be on average over 15. So if you found all the houses in Flint, Michigan and measured all of their water, it's most likely not going to be over 15. Now what they did, because they said, well, you know what, that's nice and everything, but that's only 71 residents. There's a lot of people who live in Flint. So let's say we went and did a bigger sample size. We went and found this many people, or I guess samples, and recalculated everything. Now we're going to simply redo a new confidence interval and then make an interpretation based on this new problem, which means that we need to go back and get our calculator, copy it, bring it back to the problem, and paste it somewhere. How about I drop it over here? Double click where I need to. Great. So now we're going to simply plug in numbers. In this case, they're giving us all the values to use. They're telling us that we have a sample size of 23171, 23171. We have the mean of that many households was 17.09, 17.09. And we have a standard deviation of 281.4. And we want a 99% confidence interval again. And so now we have a confidence levels of 12.328 all the way up to 21.852. So now the question is it possible that it exceeds 15? So the answer to this question is yes, it's possible. How come? Well, because there are some numbers in here that are bigger than 15. It could be 15, it could be 16, 17, all the way up to 21. So it is possible that the water is toxic. But notice my language here. I'm not saying that I know the water is toxic. How come? Well, remember, we don't actually know what the average is. All we know is it could be as low as 12 point something and 21 points, or as high as 21 point something. So it may in fact turn out that the water, if you went to every Michigan home, that the water is only 13, right? Because that's in the interval. That's a legitimate number. It could also be 14. It could even be 12.5. All these numbers are just as likely as the number 20, 19, and so forth. It doesn't actually matter that if you think about it in a continuum sense, that if you go from 12 up to 21, that 15 is obviously, this is only 3 numbers wide by range, and this is 6 numbers wide. It doesn't matter that there's more numbers on this side. That's a faulty reasoning. Every single number has an equal probability of happening. It's a uniform distribution. So every number from 12.3 to 21.8 is equally likely and equally legitimate. So we cannot just simply say, well, there's more numbers that are higher than 15, so therefore you're more likely to have an unhappy or unhealthy water supply. We don't know that. We know that every number has an equal chance of happening. And so you're just as likely to have a number that's higher than 15 as you are to have a number lower than 15. All we know is that now, based on our information, we can not guarantee, but we can say that it's possible the water is actually toxic. While based on our previous information, we would say we're fairly confident based on our information that the water is not toxic. And so now with a bigger sample and more information, we can say, oh, actually, the water might be poisonous. And what you would actually do, because now it's perceived as possible, we would do something called a hypothesis test, which I'm going to go into next Saturday and show you how to set those up and how we can then verify, based on this kind of information, Do we have a case where the water, in fact, is poisonous, and should you stop drinking the water and revamp the whole water supply? Or do you just have a few cases where people are really, unfortunately, unlucky? If you look at our data, a lot of people have safe water. There are a few cases where the water is really, really dangerous and bad. That 42 is a very high and toxic level, 28 and 18. But if I think about this in terms of the typical household, it appears the typical household is safe. There's a few cases where the water is really, really bad. And so should I necessarily go through and revamp the whole entire city's water, or should we just figure out why those particular houses are so high level? Because that's the kind of choices that we would have to make as a business manager or city manager. But based on this information, we can conclude that it is possible that the city water is toxic. We just can't say that it is for sure. Starting at the question, you immediately know what to do. You want an interval, so it implies confidence interval for the mean on how much money they spend on their dogs. We go to our calculator, we copy the calculator, we come back to the question, we paste it in, and then we spend our time interpreting it as always. The interpretation is the biggest part of this class, especially for this test. Anybody can build a calculator. Yours might look different from mine if you do it a different way. You go to YouTube or you follow your instructors. I just prefer to do it in this format. But anybody can build a calculator. The harder part is, what does this stuff actually mean and what's the implications? Let's plug in what we know. We're told the mean. The average person spends $139.80. We're told the standard deviation. And we're given the sample size, 40. Last thing we need is our confidence level, 95%. And there we go. So we can say we have a confidence interval of 131, 68, 147, 92. And of course, we're talking about money, so I'm going to add some dollar signs here. Don't lose the easy point. You're talking about objects, so make sure we describe it appropriately. And so we would say we're 95% confident the average amount of money families spend on one dog per month is between $131.68 and $147.92. And there we go. Part C. Suppose we find out we know the mean amount for reptiles is $116.63. Can we say that they spend more on reptiles than they do dogs? Well, we can in fact say that it's not true. No. In fact, reptiles appear cheaper than dogs because 116.63 is smaller than the overall interval. And so if it's smaller than both numbers, then we can confidently say, because we don't know how much dogs cost, we just know it's between these two numbers. And so this being less than it means it has to be cheaper because it's cheaper than the average cost. And so if the average reptile costs you $116 and the average dog costs you somewhere between $131 and $147, clearly it's more. The dog is. So that means that we can actually say that, in fact, it's not that reptiles are more than the amount we spend on dogs. It's going to be less because it's smaller than both numbers. Now, what would have happened if the reptile was $132? What if instead this number was 132? Well, now we can no longer make that claim. We can't claim anything if that was the case. How come? Well, 132 is in our interval of possibilities. Remember, we don't know what number is in here, so it's just as likely to be way down here at the smallest number as it is to be way over here on the highest number. And so if it's in the range, we can't claim anything. It's just a possible value. They could actually both be 132. It could be the dog's $131.70, or it may be the dog's 140 bucks. We don't know. We know it's between these two numbers. And so if that value, if the cost of the reptile is between those two numbers, we don't know any kind of comparison beyond the fact that they may be the same thing. That's all we would know. But in this case, 116 is definitely smaller than both numbers. And so we can confidently say that reptiles are cheaper than dogs. Down in part D here, we see that Jason is saying that he thinks the average amount is $145. Does this appear reasonable? Well, is 145 between our two numbers? Absolutely. So yes, we don't care that it's on the upper end and almost outside the range. Any number in that range is reasonable. So yes, it is possible. That's all we know. We don't know if it's a high possible, low possible, because any number in that range is a legal, valid number. So he could have said 147.91, and we'd say, yeah, it's possible. Reading bottom to top, construct and interpret a 95% confidence interval for the mean. Boom, we know what to do. Go grab your calculator, copy it, bring it into the question, paste it somewhere, and then start answering what we know. And I love the fact that Excel carries all your formulas over so you don't need to constantly retype everything in. Okay. So let's see. Let's pick apart for our information. We can see standard deviation, we can see average, and we can see our sample size and our confidence level. There's our four measurements. Just plug it in. Average 20.85, standard deviation 13.41, sample size 50, confidence level 95%. Poof, we have it. Our confidence interval is 17 point, let's just do 3 decimals because it's what I already set to, 24,661. That's how I'll represent it. And now if I want to interpret it, I would say I am 95% confident the average amount of time parents spend with their toddlers in 1 week is between 17.039 and 24.661 hours. And so in a given week, it appears that parents spend between 17 and 24 hours with their kids. Reading bottom to top, we already know what to do. We know to go grab that calculator. We're going to copy it. We're going to jump into the problem and we're going to paste it. You save so much time when you read these word problems starting at the bottom. That way you at least know what to set up and what you need to dig through the question for, because all these problems going forward are going to be essentially word problems. And as a person like myself who has a difficulty reading, you will save so much time and energy just starting at the bottom. Because you'll see, right, here's my standard deviation, here's my mean, there's my sample size, so I stop reading. I get to skip 2 sentences altogether that don't matter. They don't help me at all with building my confidence interval. They may help me in the long run with that interpreting part, but not for the crux of it all. Mean was 8.25. That's not an 8, is it? There we go. Let's just verify there's actually a decimal there. Am I erasing this little thing? Yep. And then standard deviation was 0.25. Sample size is 100. Confidence level is 99%. And there we go. We now know our average is between 8.1843 or whatever level of precision that you need to round this to. And so if we were to interpret it, we would say the mean discharge with a, sorry, we are 99% confident the mean discharge for all capacitors of this type is between 8.1843 and 8.3157 seconds. Have no idea what a capacitor is, but it takes 8 seconds for them to discharge. Is essentially what I'm saying. 8 and change, obviously. Keep peeking at the chat real quick. Perfect. So if you start at A, the question is, you'll see that I'm talking about a confidence interval for proportion. So boom. That would be a flag that we can't do it the way we've been doing it because this is a proportion question. So that means that we're going to need some other kind of measurements. Well, first off, though, how would I know that if they didn't even tell me? They just say make a 95% confidence interval. Well, if I look up here at the above facts, notice that there's no mean. There's no standard deviation given. So there's no data set to calculate those things. So I definitely can't do it by the means. But we do have a ratio. 256 people use Facebook out of 475. So I do have a proportion. We use this little arrow when we're talking about a sample proportion. We call it p hat. And so we have 256 out of 475. So this is a big red flag that even if they didn't tell me this, and they just say make a confidence interval, that I should be setting it up using proportions because I have a relationship, a fraction. So the cool thing, though, that I talked about last week, but I didn't get to show you, is that if you go into an old document, you can still highlight everything, copy it, and you can paste between spreadsheets. And all of your formulas come with it. So once you make your calculator on any document, it will follow you as long as you can copy and paste it properly. And so notice all my formulas from last week, they're all here still. And so I don't need to remake this thing over and over again. I just need to go back and access it. So those who came last week, you already have this calculator handy. You just need to go grab it and paste it in and then plug in what you know. For those who weren't here last week, send me a message and I will send you a copy of the recording so you know how to build this yourself. Here we go, though. We have p hat, that's that fraction relationship, 256 out of 475. And we have our total sample size. That's the total group, which is 475. And we have a confidence level because it's given to us as 95%. And notice proportions only requires 3 inputs. And so now we're told that our confidence interval is from 0.494 up to 0.584. And so there's my proportions confidence interval. I am 95% confident the proportion of all US adults who use Facebook for news is somewhere between 49 and 58%, roughly. So now read part B, get some engagement from you all, and decide if this statement is a valid statement, invalid argument, or not a valid argument. Do you agree that it appears the majority of people use Facebook based on our numbers right here for news? Put it in the chat. I'm going to give you about a minute or two. Read that question and decide, do we want to claim that a majority use Facebook for the news? Not any personal feelings behind it, but based solely on the data. Let's peek. Good. Yes, you guys are all nailing it. The fact that, remember, the whole point of confidence interval is any number between these numbers is valid. And so it's just as possible that it's 49.5%. I don't know why I did 2 decimals. Or that it's anywhere from 50 to 58.4. So even though there's more numbers above 50%, it's possible that it's under 50%. So we can only use words like majority and minority when both numbers, when this is completely over 50%. Majority in mathematics is a very precise meaning. It simply means greater than 50%, not even equal to. And so unless both numbers are bigger than 0.5, we cannot claim that. Likewise, minority is the same thing, but in reverse. It's when both numbers are less than 0.5. So we can't claim minority or majority in this case because they're not either both bigger than 50% or both smaller than 50%. So we can't claim a majority or minority. It may be true. It might be that 50 to 58% use, or more than 50% use Facebook for news. But it's also just as likely that it's on this end of it, and that is closer to 49%. So we have to say we disagree. It is just as likely to be under 50% as it is over. Now, if this first number here, this 0.494, if that number was something like 0.501, then we could make this claim because we don't know where the answer is, but it's somewhere bigger than that number and somewhere smaller than that number. And so it's legitimate in that case that you could say a majority. But the fact that one of the numbers is less than 0.5, I don't care how less than 0.5 it is. The fact that one number is less than 0.5 means that you cannot make this guaranteed claim. All right, last one. I hope you're finding out confidence intervals, at least in my opinion, are kind of fun. The harder part is the interpretation, but the actual calculation isn't so bad. Especially once you set your calculator up, it's a matter of copying and pasting and then plugging in your numbers. 90% confidence interval for the means. Let's go grab that calculator. Let's copy, jump into the last page here, paste it somewhere, expand our cells, and now plug in what we need to know. So let's see. Means is 29.8. Okay, 29.8. Standard deviation, that's right here, 4.37. Sample size, random sample of 18. Okay, 18. And yeah, you might be screaming, James, that sample size is under 30. How can we do standard error calculations? How can we do the S over E and all that, S over square root of N? Well, because the population's normal distributed, right? CLT requires either condition. You don't need to remember that. It's just a nice little throwback to test 2. But anyways, confidence level is 90%. They're not going to make you recheck that until the final, at least. So now that we have the confidence level, we have our confidence interval. We have our margin of error calculation if we need it, but more importantly, we have our confidence interval right here. 28.008 up to 31.592. And of course, if I wanted to represent these other mechanisms, I could have said by margin of error format, 29.8 plus or minus my margin of error to whatever kind of rounding you need to do, or by inequality notation. They can ask you to do it any way technically. We just usually just do the first format. No real reason, it's just how the department decided they want to do it for this class. But all three are legitimate methods. I show you because sometimes you'll see one of the other two methods in your book randomly, and they expect you to understand that these all mean the same thing. And so these are the three methods for representing a confidence interval. We have it by interval notation, margin of error notation, inequality notation. But anyways, let's actually do the interpretation step now. In this case, I'll actually write it out. I've been saying it a lot, but I have not been writing it. And so forgive me, because Writing is not always fun for me. But let's say we are talking about 90% confident. So we are 90% confident that the true population mean length of unemployment, mean length of unemployment for all people who, notice I'm just stealing what it says, mean length. I'm stealing this information right here. I'm taking it directly from the question. Of all people who filed, and this is what you will do. You just literally verbatim repeat what it's telling you. Who filed during the years 2015 to 2017 is, and now I can plug in my findings, is, let's just say between 28.008, 31.592, and our information was all about weeks, so we'll say weeks at the end. I'm going to use the word and not be so lazy there. 31.592 weeks. And there we are. There we are. We are 90% confident the true population mean length of unemployment for all people who filed during the year 2015 and 2017 is between 28.008 and 31.592 weeks. So I have no idea how long it was for every single person on average. I just know that it's somewhere between those two numbers. And of course, I'm only 90% confident, which means that I'm admitting that this method only works 90% of the time. And if I wanted to be more confident, I would have to widen my calculation. Just to remind us what I'm saying now is notice my values. I say it was 28.008 and 31.592. If I want to be more confident that I know the actual answer here, what I would have to do is deal with the fact that it's going to result in a larger error range. So if I want to be 99% confident, notice now I'm saying that's anywhere from 26 to 32. These are further apart. It went from being about 3 weeks amount apart to now being about 6 weeks apart. So I widened the possible acceptable values. Where before I was saying the answer is somewhere between 28 and 31, I'm now saying it's pretty much between 26 and 32, roughly 26.8 and 32.8. So I made a wider net. If you think about the logic behind that, why that is, if I told you to guess my number, and I gave you a range to guess my number, like I have a number in my head, and you had to guess it, but I allowed you to pick a range. If I said you had to guess it, but you're allowed to only be off by 10 numbers. So you can say like your number's between 10 and 20, or 20 and 30, or 21 and 35. Would you be more confident with that kind of range? Or if I allowed you to have a 100 number level, like you can say it's between 10 and 110, 20 and 120. Well, hopefully you'd be more confident you can get my answer right with a 100 range. And so notice that the higher the range, the more confident we would become. And so by raising the confidence level, we naturally widen the interval to kind of accommodate that. That's what's going on there. Yes, that's exactly right. The higher the confidence level, the wider the confidence interval. But now what would happen if we increase sample size? What happens to the confidence interval if the sample size gets bigger? Well, think about what that's telling us. If the sample size is bigger, will the actual sample measurement be closer or further from the population measurement? Well, the more people we know, the closer we are to the population. And so the larger the sample that you get, the greatly shrinking of the interval you have. Because the sample becomes closer and closer to the population itself because you have more and more of the population. So here's a nice fact that they always ask you every year on an exam. And let's just make a little diagram somewhere. But essentially, if the confidence level increases, the confidence interval also increases, which means that the confidence interval decreases, the confidence interval also decreases. They always change in the same way. However, sample size does the opposite. The larger the sample size, the more sure we know the confidence answer, the interval answer, so the less of an interval you're going to need. So it's going to shrink, which means if I shrink my sample size, we have less certainty of guessing the interval, so we're going to need a bigger interval. So for sample size, it always changes the opposite way. So if you increase sample size, you're going to decrease your interval width, and vice versa. And so if I went down to a sample size of like 3, this gets much further apart because we're going to need a more of an error allowance to compensate the fact that we have such a little bit amount of the population. But if we have a very big sample size, we're very, very confident that that measurement is more representative of the actual population. And so the interval shrinks. But there we go. Nice little fun fact. They ask you this every year. So just so you have it. All right, my friends. I'm going to stop sharing. I'm going to stop recording.